the new homework or practice problems online? Good. So let's recall what we were doing. So we had a domain G. Numbers. Then for any f we had this wonderful Cauchy integral formula, which said that for any disk K centered somewhere, says that it's completely inside G. You can express the value of the function at a given point inside disk. As an integral, as Cauchy integral, with a certain factor which comes from integration, and then integral over the boundary of the disk. Z minus Z, and as I explained last time, we talked about it's in a way a miracle because you're expressing the information totally inside the disk via something you know along the boundary. So, so today we'll apply. Let's call this Cauchy integral formula. So we apply Cauchy integral formula to prove the following fundamental thing. If f is holomorphic in G, it follows that f is infinitely differentiable in G. So in other words, for any z in G, any derivative like this exists. Which is, of course, crucial difference from what we have in real analysis, real calculus. Also, we'll get formulas for the derivatives in the similar terms to the ones above. So tools. So we know already that if sum of series centered at 0 or centered somewhere else, converges absolutely in some disk. Then it's so the sum given by the sum has a derivative everywhere in the disk, given by similar series, given by term-wise differentiation of term-wise applying. And this series for derivative have the same radius of convergence. So the plan is to given f, which is holomorphic in G, represented as sum of C's in some disk around every point. So then, of course, from what we know already, we'll get that the function is differentiable infinitely many times. So, in a way, one can introduce equivalent but different word. A function is analytic if it is a sum of series. I mean, power series. So analytic functions are, by our chapter 1, are infinitely differentiable. And we need to see that every holomorphic function is analytic. And that's what we'll do. So this is one idea. Then use Cauchy integral formula to get this series. And we need analytic tool. So we need a new analytic tool. Uniform convergence. Of sequences of functions. So this is like general analysis and recollections. I am sure that you talked about this in your course of real analysis, but there's no actual difference. But so what we're talking about in the book is 4.1 and 4.2. So I'll talk extensively and rather slowly about this uniform convergence. Certainly define it and whatever. Let's start from the very beginning of this analytic story. So definition. Imagine we have some M, maybe a subset in C. Right now it's not important whether it's open or it's a curve or anything. And we have a collection of functions. So we say that the sequence of so n is just integer numbers, positive integer numbers. So the sequence converges pointwise to f, again a function like this, if, well, for any point x in M, the limit for n tending to infinity of numbers f n of x is f of x. So let me write this in this epsilon delta language, which is so boring, but it will show the difference from the other type of convergence. So, remark, this means explicitly the following: for every epsilon greater than 0, there exists n which depends on a given point, and this is important, for every n greater than n of x, absolute value of the difference of n of x minus f of x is less than epsilon. So this type of convergence is not very useful for many reasons, but one of them is pointwise convergence. Is too weak. In particular, even it is wrong in general that if all Fn is continuous, for every n Fn is continuous, then F is also continuous. So this is wrong. So this type of convergence doesn't even preserve continuosity property, and of course also bad behavior with respect to integration and so on. So this is too weak. We won't talk about this convergence. Instead, we introduce a different definition, a stronger one. Again, in the setting as before. And is a subset of C. And Fn is a sequence of functions. So Fn tends to F, which is a function M to C. So uniformly in M if so look at epsilon delta language. So you for every epsilon greater than 0, you can choose n, which is one choice for all points in M, such that for every n greater than n and every x in M, the absolute value of Fn of x minus f of x is less than epsilon. So the difference is that this number is chosen once for all points in the set. Now the theorem, which is easy and well known in real analysis. So suppose that again Fn and f are functions on some set M, and Fn converges to f uniformly on M. And all Fn are continuous. It follows that f is continuous. So let's prove it, or maybe sketch of the proof. So what we need is for every point x node in M and every epsilon greater than 0, we look for delta such that if the absolute value of x minus x node is less than delta, then absolute value of f of x minus f of x naught is less than epsilon. So this is our goal, and it's done like this. So we choose for a given epsilon 0 n such that absolute value of fn of x minus f of x is less than epsilon over 3 for n greater than n. Everywhere in M. So here we use uniform convergence. Then so for a given x naught, since fn is continuous, let's say that we chose one n like this, n is greater than n, there exists delta such that for all x close enough to x naught, absolute value of fn of x minus fn of x naught is again less than epsilon over 3. Now, for the same delta, so for the same absolute value of f of x minus f of x naught is absolute value of f of x minus fn of x plus fn of x minus fn of x naught plus fn of x naught minus f of x naught. So then we use the standard inequality, and we see that this is less or equal than absolute value of fn of x minus fn of minus f of x plus absolute value of n of x naught minus f of x naught plus absolute value of f n of x minus fn of x naught, and each of these is less than epsilon over 3, so this sort of thing is less than epsilon. We're done. It's standard thing which by now I think each of us should be able to cook up without looking in the book. So at least this property is satisfied. And now we'll discuss convergence of series of functions. So, yeah. So this is the definition. So in the same situation, fn c sum n greater or equal to 0 fn converges uniformly to f, or maybe s, sum of series, so it should be s. If partial sums Sn of which is defined as partial sum converge uniformly to S, and this is exactly the form of this uniform convergence we'll use. Now there's a theorem which is called Weierstrass M criterion. So again, we have many functions, and suppose that absolute value of fn at any point is less than an, and sum of an converges as sum of non-negative real numbers, then sum of fn's converges in again, I won't go into great detail, but sketch of proof is so by standard considerations, uniform convergence follows from the fact that for every epsilon greater than 0, there exists capital N chosen once and for all, such that for every n m greater than capital N, sum or n less than sum from n to m f by absolute value is less fn is less than epsilon. So, I mean, this is standard thing. This is for any series. So then we can just use the estimate. So we know, again by convergence, that for every epsilon greater than 0, there exists n, for every n less than m, sum from there's a from notation. Summation is over some new index k. K equal n. And the same here, k equal n to m. A k is less than epsilon. So choose this n, then absolute value of this sum k equal n to m fk of x at any point is less or equal than sum of absolute values less or equal than sum of AKs and less than. So this is the proof of criterion, and now we'll use it for the following. So theorem. The convergence of absolutely converging power series is uniform. So suppose that sum a n z to the n greater equal to 0 converges absolutely in A0 rho, then for every smaller disk completely sitting in A0 rho, for every the convergence is uniform. Yeah, I don't know. I'm getting slightly bored at this point, but I'll just write the hint. Use the previous theorem. For estimating series. Some absolute value of an r to the n. I mean, this is the series you will substitute into this theorem. Good. Now, so all this was, so it looked like classical analysis, and there'll be more of it, but now we come to the next technical, maybe the last technical thing we'll need. So the last technical thing we need is uniform convergence and integration. So as I said, the usual point set convergence doesn't work very well in this setting. So theorem. We have some curve, which in our case will be just the boundary of a disk, a circle. Later on, when we start applying it, so we have a curve, maybe AB. Somehow the book doesn't want all intervals to have the same length. To see a curve, and we have a sequence of functions, so this is the image. It's a subset in C, and this will be our M. So we have a sequence of functions. Defined on this curve. Continuous functions, whatever. And suppose that they're converging uniformly to f, which is another function on this uniformly. Then the limit of integrals of Fn on gamma equals integral of the limit function on gamma. Okay, let me put this as A. And B is the same for summation. So in the same setting, if sum of Fn n greater equal to 0 uniformly converges to S, which is the sum function, then we can integrate again, interchange summation and integration. Okay, so remark, B follows from A. Immediately, just apply A to the sequence of functions Sn, which are partial sums. So we need to prove A, and we'll do it. So proof of A. So we choose, so for given, we choose epsilon greater than 0, get n, whatever n greater than equal n, any x is on the curve, absolute value of fn of x minus x is less than epsilon. Yeah, so then or maybe even better, for every n and what? No, okay. Like this. So then we take absolute value of integral over gamma of f minus integral over gamma fn, and this is of course absolute value of and then it's estimated by and this one is estimated by epsilon times the length of the curve, and of course it can be made as small as you want. Good. So of course we used uniform converters here, otherwise it won't work. Good. I think this is all I wanted to say about uniform convergence. So end of stupid considerations which would work basically in any context. Let's return to something related to complex numbers. So let me introduce an invariant for so we is a domain in C, will be studied F is holomorphic in G, and eventually come to the theorem I talked about. So I just want to introduce a new concept for any point in G. The maximal disk around A in G is defined like this. So K of A rho. Here rho is defined as follows. So it equals infinity if G itself is the whole complex numbers. So this is not interesting. Otherwise, the complement of G exists, and then we define rho as infimum of distance from A to a point outside of G. Okay, so question, do you understand why rho is not 0? So in principle, rho is just a number, and by definition, being a distance, it's greater or equal to 0, but it's infimum, so why is rho greater than 0? G is not arbitrary, it's a domain, which means that for every A in G, there exists some disk, R, totally inside G, which means that this rho is estimated from below by some R. So R, here R is strictly greater than 0. So then rho is greater or equal than this R. Okay, so I defined maximal disk around this point, and then so let me formulate our main theorem, and this will be basically everything before the break. So we have G numbers, and F is holomorphic function. Then for every point in G, and every disk which is completely inside this disk I talked about, F is given as sum of series. So it's F is infinitely differentiable at a it's given as sum of series, which you expect. And the important thing is that, so converges uniformly, whatever, And the important thing is that we have explicit formulas for these partial derivatives. Is given by n factorial over 2 phi pi. Similar to what we had before. At the end of the previous lecture, I announced generalization of Cauchy integral formula for different powers, and I'm writing it. Sorry. To n plus 1 dz, where z node is in K R. So we get by similar formulas not only the value of the function at every point inside this disk, but values of all derivatives. And this is somehow the huge difference from real situation. The function is infinitely differentiable, and all derivatives can be calculated using the values at the boundary of the disk. Okay, so let me say a few words about the tools in the proof. So first of all, of course, it's Cauchy integral formula for f, which is called morphic G. Second, it's sum of series, so expansion. And third, change of integration and summation in uniformly converging series. So the last statement is over there, and over here. And well, after the break, I'll start by discussing this one, and then we'll prove the theorem.